Hi, in this video we're going to be looking at the solutions to the Couloumbs Law worksheet. Quick reminder, Coulomb's Law shows or illustrates the force between two electric charges, and it's only two electric charges. So if you have more than two, you have to use Coulomb's Law multiple times. But for a quick reminder, the force between two electric charges is found by taking the electrostatic constant, which you can find in the front page of your reference table, but it's 8.99 times 10 to the 9th Newton meters squared over Coulomb squared, and you multiply that by the product of the charges, so Q1 and Q2, and then you divide by the square of the distance between them. Remember, we need to be in coulombs for our charge, and our distance needs to be in meters. So if we look at number 1, how much does the electric force between a pair of charged bodies change when the separation is doubled and then tripled? Now, there's a unique way of doing these because they aren't really asking you to find a solution. They're asking you for it to change. I encourage you, use the equation so you know that F is equal to K, F sub E, let's get rid of that, is equal to K Q1 Q2 over R squared. But since they aren't actually asking us to calculate anything, just make up numbers. Let K, and I'll put this in green, be 1. Let Q1 be 1. Let Q2 be 1. And let R be 1. Don't forget to square it. And obviously that's going to give us a force of 1. Now, if we double the separation, I'll put this in blue, that means K stays the same. And I'll leave that K stays the same, Q1 stays the same, Q2 stays the same. And now our separation now becomes 2. Don't forget to square it. And so now that's going to be 1/4 when we calculate that out. So it's going to be 1/4 as much as what it was before. So if you double the distance, it'll quarter the force. Now, if we triple it, obviously we go 1, 1, 1, because we didn't change the K, the Q1, Q2. But now, and I'll put this in purple, now our distance tripled, don't forget to square it, which is going to be 1/9 as much. So it's an inverse square relationship, and if you double the distance, it's going to be quarter of the force. Triple it, 1/9. Quadruple, it'll be 1/16, so on and so forth. We can do number 2 the exact same way. We'll leave the same equation. The force, the electric force, is K Q1 Q2 all over R squared. And again, we'll go with the same thing. Let K be 1, Q1 be 1, Q2 be 1, and R be 1. Don't forget to square it to give you 1. Then it tells you that we're going to double one of the charges. So I'm going to let K stay 1, make Q1 2, and leave Q2 back to 1. I know it sounds confusing. And then we're going to leave the distance the same as well. And so when we do that, we find that it's going to be double. So if you double one of the charges, you will double the amount of force. If we now triple one of the charges, again we have 1, and we'll now change Q1 to be 3, leave Q2 to be 1, and the distance is still going to be 1 squared. Now it's going to be 3 times as much. So it's a direct relationship between the charge and the force. Now we get to number 3. Number 3 is a huge step up. Okay, and I probably should have put this one last, but we'll do it because actually the next ones 4, 5, and 6 are actually 4 and 5 are actually a lot easier than this one. But let's take a look at it anyways. It tells you the most common isotope of hydrogen contains a proton and electron separated by a distance of about 5 times 10 to the negative 11th. So let's guess this. So we know our R. Remember, R is the radius of the circle, but it's also equal to the distance between the two objects, okay? And so, like I think I explained it before, if the distance between the front end of this pen and the back end of this pen is 0.5, if it goes in orbit around there, it is still the radius. So the distance between is still going to be the R value, the distance between the centers. And if you look at your reference table, they actually label that as such. So our R is going to be 5 times 10 to the negative 11th. And that's going to be in meters. And they give us the mass of a proton. So I label it as M sub P is 1.7 times 10 to the negative 27th kilograms. And they tell us the mass of the electron. And that's going to be 9 times 10 to the negative 31st. Now this isn't exact, and if you look on your reference tables, you'll see that these are not the same numbers on the reference table, but it works okay for our approximation on this particular problem. Now, they want us to use Newton's Law of Gravitation, so that's a flashback. The Law of Gravitation, F sub g, is equal to big G times M1 times M2 all over R squared. Well, we know that big G from our reference table is 6.67 times 10 to the negative 11th Newton meters squared over kilogram squared. We know that M1 is the mass of the proton, so that's 1.7 times 10 to the negative 27th kilograms. And we know the mass of the electron is 9 times 10 to the negative 31st kilograms. And then we're going to divide it by the distance between them squared. So we got to divide that by 5 times 10 to the negative 11th meters. Don't forget to square it. And when we do that, we're going to find a force of about 4.08 times 10 to the negative 47th newtons. So really gosh darn tiny. Okay? If we look at part B, it says using 1.6 times 10 to the negative 19th as the elements unit of charge. So you have to remember that both a proton, 1.6 times 10 to the negative 19 coulombs, and an electron both carry one elementary unit of charge. Okay, technically the electron is going to be negative. Okay, and so we know that we can find the force between this attraction, the electric force, by using our Coulomb's law formula. F sub E is equal to K Q1 Q2 all over R squared. And we know from the front page of our reference table that K is 8.99 times 10 to the 9th Newton meters squared over Coulomb squared. We know the charge of a proton is 1.6 times 10 to the negative 19th coulombs. We know the charge of an electron is a negative 1.6 times 10 to the negative 19th coulombs. And once again, the distance between them is the same as it was before for the gravitational one, 5 times 10 to the negative 11th meters, but don't forget to square it. And when I do that, I get 9.2 times 10 to the negative 8th. So significantly bigger. Even though it's a really tiny number, it's still much, much bigger than the electricity. And actually taking this is going to be negative, telling you that the force is going to be attractive. Now remember with gravity is only ever attractive. But with electricity, you can have attraction or repulsion depending on the types of charges. So part C asks how many orders of magnitude greater is the electric force between the two particles, the gravitational force between the two particles. So with orders of magnitude, what you want to do is you want to reduce this down to scientific notation, but you want to get it to 1 times 10 to something. So what we're going to do is we're going to round this. We're going to change this to 1 times 10 to the negative 47th. You're like, well, why would I do that? Because order of magnitude, we're only concerned about this part right here. That order of magnitude is just the power of 10. And so we want 1 times 10 to the something, and that something is the order of magnitude. If we look down here, this is going to become now 1 times 10 to the negative 7th. And you're like, whoa, how'd that happen? Well, when I round the 9.2, that gives me 10. So it's like 10 to the negative 8th, which is 1 times 10 to the negative 7th. And again, it's negative, but I'm not concerned about that because they're both going to be attractive regardless. So I look at the powers of 10. And so when I look at this and I compare these two, this one down here, the electrostatic force, is 10 to the 40th times, 10 to the 40th times bigger. Okay, and I got that by just subtracting them. So negative 47 minus 7 is 40. Okay, it actually should be negative 7 minus negative 47 to give you 40 times. So times 10 to the 40th bigger. So its order of magnitude is 40. So order of magnitude is 40 times bigger. That's how many powers of 10 bigger is it. So it is massively huge. So what that tells you now in the second one, how important are gravitational effects in this case? Almost negligible. I probably butchered that word. Okay, so almost not. Let's change it. Almost nothing. That's better. That way I can actually, you can look at it. I don't have to butcher the spelling of a word. So almost nothing. The gravitational force has almost no effect compared to the electrostatic. Okay. All right. So let's jump down here to number 4. Okay. It says negative charge of 2 times 10 to the negative 4th. Positive charge of 8 times 10 to the negative 4th. They're separated by 0.3 meters. So let's guess this. So we've got the Q1 is equal to a negative 2 times 10 to the negative 4th coulombs, because it's a negative charge. Q2 is 8 times 10 to the negative 4th coulombs, and the distance between is going to be 0.3 meters. So if I want to find the force between, I'm just going to use the Coulombs law, K, Q1, Q2, all over R squared. So 8.99 times 10 to the 9th Newton meters squared over Coulomb squared, times my Q1, which is a -2 times 10 to the -4th coulombs, and Q2, which is 8 times 10 to the -4th coulombs, divided by the distance between them, which is going to be 0.3 meters, but don't forget to square it. And when you do that, you're going to get a whopping 15,982.2 newtons. So this is a huge force, and technically it is negative, but what that negative tells you is that it's going to be attractive. And so the magnitude of the force is just the number that it spits. So that would be the 15,982.2 newtons. The direction tells you it's going to be attractive. Now, you can't really say right or left or up or down because you don't know what the location of these things are. So if one is here and one is here, it's attractive. So this one's going to be going in headed there. This one's going to be headed in this way. And so you could say, well, if I talk about the one on my left, then it's going to be pulling to the right. Okay, if I'm talking about the one on the right, it's going to be pulled to the left. But if you're just talking just attractive, you know it's going to be pulling in on both of those. If it was repulsive, pushing them out. All right, our last one here. A young man accumulates a charge of Q1 positive 2. So Q1 is 2 times 10 to the -5th coulombs. His girlfriend has a charge of -8 times 10 to the -5th coulombs. So right off the bat, you're thinking, aha, this has got to be an attractive force because one's positive, one's negative, opposites attract. And we're looking, we know the distance between, so my R is 6 meters. We're looking for the force between them. So I'm going to use Coulomb's law. So F of E is equal to K times Q1, Q2, all over R squared. And so 8.99 times 10 to the 9th Newton meters squared over Coulomb squared times Q1, which is that 2 times 10 to the -5th coulombs. It's positive. Okay, and then the girlfriend has a -8 times 10 to the -5th coulombs divided by the distance between them, which we said was 6 meters. But don't forget to square it. And so we find that that force between the two is going to end up being a -0.4 newtons approximately. And this has got to be attractive because it's negative. So you can say 0.4 newtons attractive, but if you just left it as -0.4 newtons, we would already know that it's attractive. Okay, so hopefully this gives you a better handle on Coulomb's law. And if you have any other questions, come see me. All right, have a great night. See you later. Bye.